Welcome students for the fourth lecture on vector analysis for B.Sc Physics first year, first semester. Today's lecture topic is curl of a vector field and its physical significance. So far we have learned about what is gradient, what is divergence, what is gradient. Gradient is nothing but the maximum rate of change of a scalar field at a particular point in normal direction. The maximum rate of change of a scalar field at a particular point in normal direction is called gradient. Gradient can be calculated mathematically. Operator del is taken. That operator del is operated on scalar function. There we got gradient. Gradient is equals to, if phi is a scalar function or scalar field, therefore gradient of phi, that is equals to del phi. Just you operate del operator on scalar field, there you get gradient. You are operating del operator on a scalar field, you get a vector quantity. Therefore, the gradient of a scalar field gives us a vector field. Next, when you are operating del operator on a vector field with the help of dot product, there we get divergence of vector field. Divergence of a vector field is a dot product of del operator and vector field. Dot product always gives us a scalar quantity. Therefore, divergence of a vector field is a scalar. Divergence of a vector field is a scalar. So, the dot product of del operator with vector field is defined as divergence of a vector field mathematically. What do you mean by divergence actually? The amount of flux coming out of unit volume is called divergence. These are the contents we have learned so far. Just we have operated del operator on scalar field, we got gradient, that is a vector. We have operated del operator on a vector field with a dot product, we got divergence, which is a scalar. Today we are going to operate del operator on a vector field by the help of cross product, that is called curl of a vector field. Let us see what is curl of a vector field. Here, the rotational effect of a vector field at any particular point gives us the curl of a vector field. The rotational effect of a vector field at any particular point in the vector field gives us the curl of a vector field. For that, here I am taking a two-dimensional xy plane. In that xy plane, a vector A is there. A vector field is there. That is shown with these pink arrows. Here the pink arrows represents the vector field A bar. This xy plane is specified by a vector field A bar. In that vector field, suppose I am taking a point P. This point P is bounded by a closed curve C here. You see, P is enclosed with a curve C. This curve C surrounded an area delta S. This is all about point P in this vector field. For example, at point P, this vector field undergone rotational effect, there we got a curl. If this vector field undergone rotational effect at a point P, there we get curl of the vector field. The curl of the vector field is defined as, here throughout this loop or this closed path, we are going to calculate the line integral. So the curl of the vector field is defined as the maximum line integral per unit area. The maximum line integral per unit area. At point P, suppose this vector field undergone rotational effect. Therefore, along this closed path, that vector undergone rotational effect. Therefore, we got another vector which is curl perpendicular to this plane. That field direction is specified or characterized by right hand thumb rule. Here, this closed loop is in anti-clockwise direction. Therefore, here the generated curl field is along this direction. Along this direction. You see here, direction of curl of the vector field, that is along z direction. Here this z direction, z axis direction is specified with the unit vector k cap. Therefore, curl of a vector field gives us another vector field which is perpendicular to this vector field. So curl of vector field, curl of a bar, here I have taken this field is a bar, therefore curl of a bar, that is equals to maximum line integral, which is nothing but line integral a bar dot dl bar by ds. ds is the total area here into n cap. This n cap is unit normal vector. If we are multiplying with this quantity with n cap, we are getting a vector. Therefore, n cap is the unit normal vector. It can be specified by right hand thumb rule. Here what we have seen, just we are taking a vector field in two-dimensional plane in xy plane. Here this pink lines are representing vector field. In this vector field, I am taking a point P where this vector field undergone rotational effect. Therefore, here I have drawn a closed curve. This closed curve is enclosed by the point P. This closed curve bounded or surrounded an area delta S. Here, the total maximum line integral is calculated as line integral a bar dot dl bar and divided with its area, that is a ds, that gives us the curl. So it is multiplied with n cap, then we get vector field. That is nothing but the curl of the vector field. Therefore, curl of a vector field is defined as the maximum line integral per unit area. Let us see what mathematics says. The curl of a vector field is defined as the maximum line integral per unit area, but mathematically here we are operating del operator on vector field with the help of cross product. Therefore, the cross product between del operator and vector field gives us curl. Therefore, curl of any vector field is written as curl A. Here A is the vector field, curl A, that is equals to mathematically del cross vector A. Del cross vector A. That is equal to the basic definition, that is maximum line integral per unit area into n cap. Therefore, mathematically we are going to calculate the vector field, curl of the vector field as del cross A bar, that is nothing but that is equals to the basic statement maximum line integral per unit area, that is line integral a bar dot dl bar divided by ds into n cap. This may be written as limit delta s is approaching to 0 or tending to 0, line integral a bar dot dl bar by delta s into n cap, which also gives the same meaning as this curl expression. Therefore, mathematically, if we wanted to calculate the curl of a vector field, just we have to take del operator and operate that del operator on vector field by cross product. There we got cross product always gives us a vector quantity. Therefore, del cross A bar, that is curl of the vector field, gives again a vector field. Here, for the explanation, I have considered a small area of delta S. In the previous slide, I have taken a plane area. Here, I have taken a surface area, which is having an area delta S. In this area, suppose take a vector field A bar. So, in this field, in this area, I am taking a point P. There, the value of a vector field is A bar. Here I have drawn a unit normal vector which is perpendicular to this plane along this direction. You see here, this is represented by the unit normal vector n cap. So now I wanted to calculate what is the curl in this delta S area element. Therefore, I have drawn this closed curve by C. Therefore, this delta S element is surrounded with a curve, closed curve C. Therefore, I have to calculate the maximum line integral along this curve C. Therefore, maximum line integral is, here the vector is A bar. Therefore, maximum line integral is line integral A bar dot dl bar. Therefore, curl of this vector field is maximum line integral per unit area. Therefore, maximum line integral is line integral A bar dot dl bar divided by its area, that is a ds. there it multiplied by this unit normal vector, that gives us a curl of this vector field. Therefore, curl of a vector field in this surface area is the maximum line integral per unit area into n cap. This is mathematically calculating by taking the cross product in between del operator and vector field. Here you know curl A is written as del cross A bar. Del you know well, that is I dou by dou x plus j dou by dou y plus k dou by dou z cross the vector function or vector field. Here I am taken vector field as A bar, therefore A bar is specified as AXI plus AYJ plus AZK. Here that AX is the component along x-axis, AY is the component along y-axis, AZ is the component along z-axis. This is the cross product in between del operator and vector field. This can be written mathematically as in determinant form as determinant I, J, K, I cap, J cap, K cap, which are the unit vectors along coordinate axes. Dou by dou x of dou by dou y, dou by dou z. And the I component of vector, that is Ax, J component of vector, that is Ay, K component of vector Az. So Ax, Ay, Az. This is the determinant form to get the curl of a vector field. Let us see del cross A bar, that is nothing but the cross product of del operator and vector field, that gives us curl of a vector field, that is also a vector. Here I have written mathematically and determinant form curl of vector field. Just you perform the cross product here for this vector with del operator, I cap, J cap, K cap, dou by dou x, dou by dou y, dou by dou z, Ax, Ay and Az. You know, you first take this I and dou by dou y of Az, dou Az by dou y, just dou Az by dou y, minus dou Ay by dou z, minus dou Ay by dou z into I cap. This is the first. Next, go for J cap. You have to take negative sign, minus J into dou Az by dou x minus dou Ax by dou z. But you take that negative sign and multiply, then you get dou Ax by dou z minus dou Az by dou x into J cap. Next, the last one, K cap into dou Ay by dou x minus dou Ax by dou y. This is the total expression in Cartesian coordinate system to calculate curl of a vector field. Let us see we'll get this expression or not when we are deriving an expression for curl of a vector field. For the derivation of the expression of a curl of a vector field, I am taking a small rectangular area. That rectangular area is here as shown in figure. A, B, C, D is a rectangular plane which is in xy plane, in two-dimensional plane. Here the point T is the midpoint of side AB. Here the point Q is the midpoint of side BC. Here the point R is the midpoint of side CD. Point S is the midpoint of side AD. This entire plane is characterized by or specified by a vector field A bar. In this rectangular plane, I am taking a central point, that is P. P is a central point where the vector value is A bar. Vector value is A bar. Along x direction, the vectorial component, that is the component along x-axis is Ax. The component along y-axis is Ay. So for the derivation of curl, I have taken a two-dimensional plane. In that two-dimensional plane, I am taking a small rectangular area. In that small rectangular area, I am taking a central point, a point P, which is in the at the center of the rectangular area. On the sides, I am taking midpoints on the sides as a T, Q, R, and S. This is all about the picture which I have taken a vector field. In that vector field, I have taken a rectangular area. Let the point P from point P, I am going to point R, which is the midpoint of side CD. Midpoint of side CD. Here, the side AB value is dx, side BC value is dy. Therefore, side DC value also dx, side AB value dy. The sides of this rectangular plane is dx and dy. Dx is parallel to x-axis, dy is parallel to y-axis. That's all. So here I am taking the point R, which is midpoint of side CD. Now I am going from P to R. So here the vector field is increasing. The AX value from P to R is changing. Therefore, the increase in magnitude of AX along y direction is written as dou AX by dou y. Dou AX, here I am speaking about the AX component, which is from P to R. When I am going from P to R in this vector field, the increase in magnitude of AX with respect to whom? Dy. With respect to dy. Therefore, the increase in magnitude of AX from P to R is written as dou AX by dou y into PR. The rate of change is dou AX by dou y, but I wanted to find the total increase along this length. From P to R, the side is AD is dy, but from S to D, that is dy by 2. Here, P to R also dy by 2, because P is the midpoint or central point of this rectangular plane. Therefore, the rate of change of this AX along y direction is dou AX by dou y. But the increase in magnitude, that is calculated with the rate of change multiplied with this length. Therefore, the rate of change of that AX along y axis or y direction is dou AX by dou y into the length. This length is dy by 2. Therefore, the increase in magnitude of AX along y-axis is dou AX by dou y into dy by 2. Just reorganizing the terms, that is equals to 1 by 2 into dou AX by dou y into dy. This is when I am going from P to R, the increase in magnitude of AX. For example, I am coming down from P to T. What happened? The vector field decreases. The vector field decreases. So what is the decrement here when coming from P to R? That is 1 by 2 into dou AX by dou y into dy. Similarly, the rate of change of AX with respect to y-axis is dou AX by dou y. Dou AX by dou y. But I wanted to find what is the decrement from P to T. That is rate of change of dou AX with respect to y-axis multiplied with this length. This length is dy by 2, because P is the midpoint of this plane lamina. Therefore, this is the decrement. But here, what is the net value at R and what is the net value at T? Net value of the A at R is given by already AX is there, and the increment is dou AX by dou y into dy by 2. Therefore, 1 by 2 into dou AX by dou y into dy is the increment. Therefore, the value at R is AX is already there at point P. Increment is this. Therefore, AX plus increment, that is AX plus 1 by 2 into dou AX by dou y into dy. When I am going from P to R, increment is 1 by 2 into dou AX by dou y into dy, and already having value is AX. Therefore, the net value at R is AX plus 1 by 2 into dou AX by dou y into dy. Come to this point T. Here, the value at T is already value at P is AX. The decrement is 1 by 2 into dou AX by dou y into dy. Therefore, the net value at T is AX minus 1 by 2 into dou AX by dou y into dy. For example, let us see here at point Q and point S. Now I am going from point P to Q. There is an increment in the field. Therefore, the increment is 1 by 2 into the increase in the y component with respect to x-axis. Therefore, dou AY by dou x is the rate of change multiplied with this length. There we get the increment. Therefore, this length is half of this side. This side is a dx, half of the side is dx by 2. Therefore, increment of the field along x-axis from P to Q is 1 by 2 into dou ay by dou x into dx. Already value here at P is ay. Therefore, the net value at Q is ay plus 1 by 2 into dou ay by dou x into dx. For example, at point S, here I am going from point P to S. Certainly here the field decreases. Therefore, decrement is the rate of change of the field value, the component of y along x-axis, that is nothing but dou ay by dou x into how much length? 1 by 2 dx, because P is the midpoint. Therefore, this side length is dx, half of the length is dx by 2. This is the decrement. Therefore, already the value at P is ay. The decrement is 1 by 2 into dou ay by dou x into dx. Therefore, the value at point S, which is a midpoint of side AD, the value there, the field value, the y component value is ay minus 1 by 2 into dou ay by dou x into dx. In this way, we can calculate the field values at midpoint of the sides at T, at Q, at R, and S. These are the component values. Let us see how the curl is derived. The value of AX at R is given by, we have already discussed, that is AX. This is the value at P. This is the increment. The increment is 1 by 2 into dou AX by dou y into dy. Here we are going upper direction. Therefore, increment dou AX by dou y, that is the rate of change of AX component along y-axis. Therefore, the value at R is given this expression. The rate of change of AX along y-axis, that is equals to dou AX by dou y. We have already discussed. The rate of change of AY along x-axis, that is equals to dou AY by dou x. Therefore, the point P is midpoint of rectangular plane ABCD, and P is at a distance of dy by 2 from side AB. We have already discussed this. Then the value of vector field at a point T is given by AX minus 1 by 2 into dou AX by dou y into dy. Here I am writing the line integral value along the side AB. From A to B, the line integral of A dot dl, that gives us this value at P into the length dx. Therefore, the value is AX minus 1 by 2 into dou AX by dou y into dy into how much length? Into dx length. This gives us the line integral value along the side AB. Therefore, the value of vector field alongside AB bar, that gives AX minus 1 by 2 into dou AX by dou y into dy into dx. This is as equation 1. Say this as equation 1. So, in this way, we are going to write the values, vector field values on all the sides. Now, then the value of a vector field at a point Q on side BC. On side BC. Therefore, line integral B to C A dot dl is equals to, at point Q, you see here the value is ay plus 1 by 2 into dou ay by dou x into dx, which multiplied with this side, there you get the side is dy. Therefore, the line integral value is the value at Q into dy. The value at Q is ay plus 1 by 2 into dou ay by dou x into dx into dy. Say this is equation 2. Similarly, we can write the values of the line integrals on side CD and side DA. Here on side CD, the value at point R, just we have discussed, AX plus 1 by 2 into dou AX by dou y into dx, dy into dx. So here in the picture, we are going in anti-clockwise direction from A to B, B to C, and C to D. So this is the negative direction of AB. Therefore, this line integral contains a negative sign. Therefore, the negative sign here arises due to CD is opposite to the vector component AX, because AX is along x-axis, that is in the side AB. But here we are going from C to D, that is opposite to AB, that is opposite to AX, That's why we have taken here negative sign. Similarly, the value of vector field on side dA at S, that is given by the value at S, that is ay minus 1 by 2 into dou ay by dou x into dx into this length, that is dy. So here that is taken as equation 4. From D to A, line integral value will be this also in the opposite direction of ay, because dA is in the opposite direction of ay. That's why here I have taken the negative sign. This is the vector field value on side AD. This is the vector field value on side CD, and this is the vector value on side CB. This is vector value on AB. In this way, we got all the vector fields on all four sides that shows in equation 1, 2, 3, and 4. Now I wanted to find the total line integral along the path ABCDA. This is the closed loop. Therefore, just I have to sum all these four equations, then I get the total line integral along the path ABCDA. So the line integral value along the closed loop, closed path ABCDA, the line integral A bar dot DL bar, that is nothing but this is the line integral on AB side. This is the line integral on BC side. This is the line integral on CD side. This is the line integral on DA side. Therefore, I am just adding all these vectorial values on all four sides. That is AX minus 1 by 2 into dou AX by dou Y into dy into dx. This is on AB side. AY plus 1 by 2 into dou AY by dou X into dx into dy. This is on BC side. Minus, already we have discussed about why this minus sign arises here. This is opposite to the AX direction. Therefore, minus AX plus 1 by 2 into dou AX by dou Y into dy, which is multiplied with the length dx. Next, again, minus AY minus 1 by 2 into dou AY by dou X into dx into dy. After simple mathematical addition and subtractions, we got only two terms here, minus dou AX by dou Y into dx dy plus dou AY by dou X into dx dy. Just in these two terms, I find dx dy is common. Just to take it out. And rearranging the terms, this positive term is written in front. Therefore, dou AY by dou X minus dou AX by dou Y into the common term, that is dx dy. This is, say this as equation 5, which is nothing but the line integral value in the closed path ABCD. The closed path ABCD. But the curl is defined as the maximum line integral per unit area. The maximum line integral per unit area is nothing but the curl. Therefore, the curl is written as the maximum line integral along the path ABCD, that is line integral A bar dot DL bar divided by the area of this plane, area of this rectangular plane. This side is a dx, this side is a dy. Therefore, area of the rectangular plane, that is dx dy. So, area of the rectangular ABCD, that is dx dy. Just I am dividing with dx dy with the equation 5. I got dou AY by dou X minus dou AX by dou Y. Say this is equation 6, which is nothing but the curl value in single plane, that is in xy plane. But here this value should be multiplied with a unit vector. How we can calculate the unit vector direction? By seeing this plane here, the path direction is anti-clockwise. The path direction is closed path direction is in anti-clockwise. Therefore, you apply right hand rule here. There you got the field direction along z axis, along z positive direction. Therefore, that is the unit vector is k cap, which is along z axis. Therefore, this quantity is multiplied with k cap. So this is the curl component along the z axis. This equation 6 represents only magnitude, but the curl of a vector field is a vector field. Therefore, to get the vector field along z direction, curl component of vector field A along z direction, that is written as del cross A of Z axis, that is Z direction, that is equals to the component, the value where we got in equation 6 multiplied with the unit vector of Z axis, that is k cap. Therefore, dou ay by dou x minus dou ax by dou y into k cap gives us the curl component along the Z axis. So let us see for the rest of the planes. Here I am taking the curl component along y axis. Curl component along y axis. That value will be dou ax by dou z minus dou az by dou x into j cap. Y axis representative vector, unit vector is j cap. Therefore, you multiply this entire quantity with j cap. There you get curl component along y axis. Next, curl component along x axis. The unit vector for x axis is I cap. Therefore, the dou az by dou y minus dou ay by dou z into j I cap is the curl component along x axis. Here we got all the three components along x, y, and z axes. Adding all these 6th equation, 7th equation, and 8th equation, we got the total curl value in that rectangular cuboid. That is, first the component of x-axis, that is dou az by dou y minus dou ay by dou z into I cap plus dou ax by dou z minus dou az by dou x into j cap plus dou ay by dou x minus dou ax by dou y into k cap. Say this is equation. Let us see. We have already performed the cross product when we are going to start the derivation or expression for this curl of a vector field, whether that the cross product is same with 9 or not. Let us see. Go to the previous slides where we have performed here the cross product in between del operator and vector A. Here we got dou az by dou y minus dou ay by dou z into I cap plus dou ax by dou z minus dou az by dou x into j cap plus dou ay by dou x minus dou ax by dou y into k cap. This is the curl value which we have calculated mathematically by operating just cross product. Here we have derived by using the statement of a curl of a vector field. This equation 9 is same where we have performed the cross product in between del operator and vector A. In this way, we have calculated the curl expression for mathematical expression for curl of a vector field, which coincided with the mathematical operation where we have performed a cross product in between del operator and vector A. So equation 9 is also expressed because it is the same value as in the earlier slide, in the first slide. Therefore, curl of A bar is written as del cross A bar, that is equals to I dou by dou x plus j dou by dou y plus k dou by dou z. This is the del operator cross the vector field. The vector is written as axi plus ayj plus azk. So that is written in the determinant form. Determinant I, j, k, the I component, I value, I coefficient in the del operator, that is dou by dou x, j coefficient, that is dou by dou y, k coefficient, that is dou by dou z, and I component, that is ax, ay, and az. This equation 10 gives us the curl value of a vector field, which is also a vector, as this del operator is independent of coordinate system. This del operator is independent of frame of reference or coordinate system which we have taken to calculate. So del operator is independent, therefore curl is also independent of coordinate system which we have taken. Therefore del operator is invariant, therefore curl also invariant. Therefore the curl of any vector field is independent of coordinate system which we have taken to calculate the curl of the field. Therefore curl is invariant. It is independent of coordinate system. Let us see what is the physical significance of curl. Already at the starting of lecture, we have discussed curl of a vector is due to the rotational effect of a vector field. Here we are operating del operator on vector field by cross product. We got curl. This is very simple. But this curl of a vector field gives us, if curl is there, that vector field is undergoing a rotational effect. If curl is not there, curl is 0, curl of the vector field is 0, that vector field is having no rotation at all. No rotation at all. So that field is called irrotational field. If curl is there, that is rotational field. If curl is not there, that is irrotational field. So maximum line integral per unit area is defined as a curl. That is the basic statement. That is also written here as a physical significance. Just we are performing a mathematical operation by taking del operator onto vector field by cross product. There we got curl. That is written as first physical significance here. In that, the maximum line integral per unit area. Next, the general meaning of a curl is always, it tells us the rotation. Rotational effect gives us curl. Therefore, curl is 0. That means there is no rotation with the vector field. That field is called irrotational field. There are no whirlpools in that fluid. If curl is there, that is called rotational vector. Where the fields, lamellar fields are there. Lamellar fields means where the fields can be obtained by gradient of a scalar field. Those fields are called lamellar fields. Curl of the lamellar fields is always 0. Curl of the lamellar field is always 0. That will solve in our coming numerical problems. Here, one more significance, physical significance is, if del cross E bar, E is the electric field intensity, electric field vector, that gives us dou B by dou T. Del cross E bar, that is the curl nature of electric field, that gives us, curl of an electric field gives us the rate of change of a magnetic field, which is perpendicular to the electric field direction. This is also one more physical significance of curl of a vector field. Now, let us take del cross B, the cross product of del and magnetic field. There we get the rate of change of current density. In previous case, we have taken the curl of electric field, that gives us the rate of change of a magnetic field. Here, in this case, where we are taking the curl of magnetic field, we are getting the rate of change of current density, which gives us the flow of electricity. So these are vice versa. If del cross F equals to 0, del cross F equals to 0, that means the force here, the F is force, for example, that field is called conservative field. If del cross F, for example, F is force here, then that force is a conservative force. The work done in this field around a closed path is 0. The work done in this field around a closed path is 0. Therefore, condition for a field to be conservative is curl F will be 0. If curl F will be 0, that means del cross F will be 0. Then that field is called as conservative field. One more statement also there, mathematical condition for conservative nature, that is line integral of the field is 0. That field is conservative. That's all. These are all the physical significances of our curl of a vector field. Curl is nothing but the maximum line integral per unit area in a vector field. Curl of a vector field always gives us a vector field. Therefore, curl is mathematically calculated as del cross vector field. If A is a vector, then del cross A bar is curl of a vector field. This is the statement and the definition of mathematical definition of curl of a vector field. These are all the physical significances which we have seen, and the assignment for today's lecture is define curl of a vector field and derive an expression for curl of a vector field. And the next second question is write the physical significances of curl of a vector field. That's all from right now.